So, hello everyone. Welcome back to our following module in our deep learning do-it-yourself course. In this module, we'll speak about a particular type of network architectures, which come also with a specific problem related to that. So, namely, I'm speaking about Siamese networks, which allow us to learn into different specific regime, but more generally, they allow us to do a focus on the representations that are learned by the neural networks. So it will be a bit more clear in the following slides. Should be working now. So where do we use? What are Siamese networks, and where do we actually use them? So I give you this problem, which is the problem of face recognition, where well, we have a lot of classes. So if you think that each person is a class by itself, you can potentially have a few billion classes. And usually we don't have many samples for each of these classes, right? So we have, let's say that you're using Facebook or something like that. You have uploaded just a few pictures of yourself. So in general, each class has very few samples, and there's numerous classes here. So what do we do now? I mean, we have seen before that, well, we can do cats and dogs. So we have a two-way classifier. We can do CFAR, which has 10 classes, and we've seen that ImageNet has about 1,000 classes. But do these neural networks scale up to billions of classes? Not quite. I mean, not quite in the standard setting, but we can take a different approach towards squeezing out this knowledge from these many classes with few samples. So before diving into details of Siamese networks, I'll just illustrate you some specific problems where we can apply it related to faces. So in faces, we can do face recognition, which means that given a face, we want to classify among well, a certain number of persons, or we can do face verification, which is verified that two faces belong to the same person. So, for example, you might have this as a border control where somebody checks your passport, the photo on the passport with your photo. So this is actually face verification, because on the passport you usually have an older photo of yourself, and you might use a software to compare it with your real version at that time. So all these classes can be implemented as a similarity measure, meaning that if you have the output of a network, it's a feature, so we can compare it with for an image, and we can compare it with other features corresponding to other images in a database. For example, in the case of recognition, say that you have a big database of faces, you come up with a new face from your camera. You compute its features from the network, and then you look inside this database to see which one is the most similar to them. And this is also named k-nearest neighbor classifier in a machine learning literature. So as I said, training a classifier with so many classes and so few samples per classes is really challenging. And to make things worse, usually in such use cases, new classes can appear on the fly anytime. So you enrich your data set, you have new people coming or new items. Well, I'm speaking here a lot about people and faces, but there's other types of items, for example, that can go in here. For example, like shopping items. If you are Amazon, there's always new items coming in with your new photos, and you cannot just restart from scratch and do a n-way classifier, an increasing n-way classifier, where n is the number of classes. So what we propose here is, instead of training a network to do classification, we can actually train it to compute useful features from images, allowing us to measure similarities or dissimilarities between images. So we achieve this not by, as we've seen before, you take one image, you pass it through the network, and you get an output, which is a classification decision. Here, we're actually taking a different approach, and we'll be using pairs of images. So here, xi and xj are an input pair of images, and what we do with them, we pass them through two networks which are identical and actually have the same parameters. This is why we call this architecture Siamese, because we have two identical networks. So what happens there? Each output of the network generates an embedding or a representation. Let's call it a feature vector, which is a compressed representation of our input image. So usually it's a one-dimension a vector with a dimensionality ranging between 256 and a few thousand. Anyway, it's a lot more compressed than what you would have with a regular image, which is in, let's say, 256 by 256 pixels at least. So what we do in Siamese architecture, we compute yi and yj, which are the features corresponding to xi and xj, and we apply a loss to them. So this is the regular pipeline, and now let's see what actually consists the loss. But before going into details about the loss, so whenever there will be a gradient here, you will have a gradient corresponding to xj, which will go through here, and another gradient coming through here, right? So we'll have two gradients now, but since we're speaking about the same features, we'll just practically sum them in when we do the gradient update for the parameters theta of our network F. So let's discover the most common loss that we use in Siamese architectures. There's plenty of them, but this is actually the one that made it, which is the more common, and actually it's the easiest to use. So it's called the contrastive loss. So here I'm representing a center vector here, which is my current vector, and I'm looking at the neighborhood around it. So in green I have the positive sample, so meaning it's the same face, the same person. And in red, I have faces or images corresponding to other classes. So practically, I'm always looking at the neighborhood of my input sample xi. So in the contrastive loss, we actually, as I said, we don't do a classification per se of the item, but we actually look at the relative distances between samples. So in the contrastive loss, we have actually two behaviors. One mode is when my input image and the other, my two input images come from the same class, and in this case what we want is to attract them. So practically I want to push these green items towards these green samples towards the blue one, such that okay, the very similar one will always be close to each other. So that's the intuition that if they are similar, they come from the same person, they should have a very similar representation. So here I'm representing the evolution of this loss, which is what we want actually from this loss with respect to the distance. So here, well, the handwritten x is the value of the loss. So this means that the bigger the distance. So here I'm computing the distance between yi and yj. So the bigger the distance, the higher the loss. Right? So the smaller the distance, which means that the similar are more similar the items, the smaller the loss. So intuitively, I'm penalizing it according to the distance that's between them. So the further it is, this sample, the more I penalize the network, and saying no, this should be much more closer to my query sample than the others. So this is what happens here in this loss. So as I said, we have two terms, two behaviors. So I have a behavior from when I have similar samples, so samples from the same class. So here I'm just having a t or a l plus, which is the square distance. So it's x squared. And this is the part that contributes to the loss. Conversely, when the two input samples in the Siamese network do not come from the same class, so we call it a negative pair. Here we try to repel as much as possible. So here we are trying to push these red dots, these red samples, as far as possible from my green from my current sample, the dark dots. So as I said, the behavior of the loss here is different. I'm showing it first on the figure, and then I will show it in formulas. So here we see that differently from before, it's the behavior is the loss has an odd behavior. Well, let's say odd at the first sight. So we have here a value m. This value m we correlate a margin, so it's practically this circle here. And what we say here is that if the distance is more than this margin m, I don't do anything. So the loss is 0. So I don't do anything. I don't touch it. I'm quite happy that it's quite far away from from my input point. So I'm quite happy. If this negative sample is close to my query point, my dark point here, we can see that the closer it gets, the bigger the loss, right? So if my point is very, very close here, I will have the maximum loss because I don't want it to. It's a behavior that I really don't want to have in these networks. So this is actually how we put it into formula. So it's since t is 1 when the target value is 1 when the pairs are coming from the same class, and 0 when they're not coming from the other class. We can see that when it's a negative pair, it's this part that it's occupied. And what we how it's formalized, it's this margin minus the distance, and it's all squared, right? So which means that the farther I am from the margin, like here, I will have a bigger loss. If I'm closer to the margin, so if here it's very, very close to the margin, I will have a small value here, and when I'm making it square, it will be again an even smaller value. So I'm not penalizing it too much in this realm. And from here onwards, it will be just 0. So how do we train a Siamese network? As I said, the pipeline is a bit different because we don't just put individual images and compile them into a batch. What we have to do here is to first sample some positive pairs, xi and xj. So here these two images come from the same class or from the same person. We also have to sample negative pairs. So in here, xi and xj are coming from different classes and different persons, and then we combine these pairs into a single mini batch. Usually this mini batch is a bit larger, and we at the output we look at these pairs of mini batches in order of samples in these mini batches to compute the loss and aggregate the gradients. An important thing in training Siamese networks is to properly tune these mini batches. So this is a key point in training Siamese networks, because we have to be careful in how to balance the positives and the negatives, and especially is to make sure that we don't have too many easy negatives or easy positives, which they will not bring any information. So just to say easy negatives, so the easy negatives are the ones that are here in this realm, so they don't bring anything. So my interest is not to have many of those, because I don't learn anything from there. I don't have the gradient because my loss is 0 here. So what I'm looking for is in particular hard negatives, and the hard negatives are these ones which are really hurting me in terms of loss, where that usually have a high loss, and having such negatives in my mini batch allows my network to act more, to impact more the training, to let it do what I'm wanting it to do. Right, to repel these negatives from my query point. And for the learning in the second stage, so once we have the data collection and loading, so once we have loaded these and created our mini batches as we wanted to, for the learning, we practically pass all the images through the two networks which share parameters. In most of the cases, well, at least for the experiments that you will do, is practically the same network on the same GPU. It's just that, well, we have the samples are seen as two different images, and when we do the back propagation, we will sum the gradients from the two images and then update for the weighting. So that's about it with Siamese networks. So well, we have here we have seen here that we have two images. Can we go a bit beyond? Because okay, it might be a bit cumbersome to have always just a positive or a negative. Maybe we can act here in the same time, meaning we can at the same time repel these red points and attract these green ones. So actually, this is possible. So the way people do this is with researchers do this is with what we call triplet architectures. So here, well, it's kind of obvious from the name. We don't have pairs, we have triplets. And we have an input image xi, and then for it we have a positive image and a negative one. Right. So the pipeline is more or less the same. We pass them through this network with shared parameters, theta, and we look at their outputs, their output vectors y, and we will compute a triplet loss. So how does it look like this triplet loss? So just to be to be clear, this input point xi, we call it an anchor, so it's the central point, and the other ones, it's easy, it's negatives and positives, and we want to with this loss, we want, as I said, in the same time to attract the positive and repel the negative at once. So I just a recap here on the notations. Yi is the output vector of the network for sample xi, and similarly for yi plus and yi minus for the positive and negative samples. So as I said, the triplet loss is also a function of distances like the Siamese loss. So we look at these distances. Here in this case, I consider them Euclidean distances, but you can apply it to other distances if you want, as long as they are differentiable. And I'm computing this the loss like this. So again, I have a margin, which is here. Well, again, I call it M. And what it does here is that it looks at the distance as a positive, the distance between the positives and the distance between the negatives. And what it actually encourages is that the distance between the positive samples should be always at least by margin M smaller than the distance with respect to the negative. Right. So this loss is quite intimately tied to the contrastive loss that we've seen in Siamese networks. So actually, if we look, if we take two pairs, xi plus and xi x minus, a positive pair and negative pair at the time with targets 1 and 0, we can actually rewrite the contrastive loss in a similar manner, because we have so here, if you remember, we have the t, and here was the 1 minus t. So if we just discard this t term and we put them in we could actually have it here. Considering these two samples at the same time, we actually end up with the contrastive loss. So it's a straightforward extension of the contrastive loss. How do we train these? So it's quite similar as before. We sample mini batches of triplets. So here, well, we have to do a bit more tuning to make sure that for each sample we always have a positive and a negative in the same mini batch. But usually this is relatively well. You can look at the samples in your mini batch to fetch those negatives. We do a forward pass on all these three samples on the corresponding networks, and then we compute the loss over all samples and sum the gradient for updating weights. So I'm giving here a very, very toy example on how it works in practice in Pytorch, such a Siamese network, and I think it's quite compelling. So here I have a Siamese network on the left and a triplet network on the right. I'm defining here an embedding net. So here you can take ResNet 50 or VGG16. So just for the sake of simplicity, I just defined another network there that outputs a vector. So you can consider ResNet 50 as you used in the first class. And when I'm defining the forward, I can see that I have in the input two images, right? Two samples, x1 and x2. I have an output 1, which is the output of embedding net, and an output 2, which is the output of the same embedding net, as you can see. So it's always the same network. Usually we have these two representations to a Siamese more for the sake of graphic illustrations, and well, to make it more illustrative and to understand the behavior of the network. But sometimes this can be confusing. So if we say shared parameters, it means that it's exactly the same network. Right? So we have always here embedding net, and it outputs these two outputs that will be fed to the loss at the end. So in the triplet net, it's exactly the same, just that we have another sample x3. Which is also goes through the embedding net, and we will return output 1, output 2, output 3. So that's about it in terms of. So well, here this function you will see later on in the practical. What does it stand for? I added here just to know that what we care at the end after training is to have feature vectors representations for our image. Because well, at test time, when we'll do inference and predictions, we will not feed the network pairs. We'll just feed one image at a time and to take its feature vector. So there's a difference between how we train these networks and actually how we use them in practice. So in practice, it's as a feature extractor. That's how we use them, and then we create a data set of feature vectors for our image data set. And you will see in a few weeks from now that we can actually do a bit even more on top of these to fine tune them, and actually in the end use them for classification. But you'll learn more about that in the upcoming weeks. So as I said, well, a very important aspect in Siamese networks is to deal with the negatives. So we could actually see that after a few epochs, if we just randomly select our images, it will be quite easy to satisfy this inequality loss especially for the triplet loss. And gradients in one batch can get quickly to 0, except for these hard cases. So random sampling is actually inefficient to find these hard cases. So what we actually do, we train for a while, and then we freeze, we stop, we take all our data set of images, and we do a feature extraction. So we compute feature vectors for our data set, and then we look for hard negatives. So we select, based on this distance, we select different negatives. So a strategy for selecting these hard negative samples is to do hard triplet mining. So the goal is to sample negative samples such as the distance between the positives is bigger than the distance between the negatives, and even a margin. So it's exactly the other way around, right? I mean, we wanted to have the distance to have the distance between the positives to be smaller than the negative distance plus but minus a margin. So actually, we're looking for really extreme cases, right? And we do that, as I said, every few epochs or a few iterations. Sorry, we select many pairs like that, and we feed them through the network until the next freeze, which will be in a couple of tens of thousands or thousands of iterations. When we do a step of mining. Another strategy of doing negative mining is semi-hard triplet mining and sampling. So we practically relax a bit the condition here. We will look not necessarily of positives with way bigger distance than the negatives, but just positive distances which are bigger than the negative ones. So this should be easier to find out. So I will head towards the end with some applications of these types of architectures. So as I said, they're quite specific, but they are really useful in practice. And so one of them, the obvious one is face recognition. So I think most of the face recognition algorithms, good or bad, but I mean used for good purposes and bad purposes, for security or for spying people, are actually based on these kinds of techniques on metric learning. So we use them. They are used quite heavily for face recognition. So you might have seen different face recognition algorithms out there during your previous courses, and at least until a few years ago, most of them would be able to recognize a person by if they were looking at the camera. But actually now these deep learning based face recognition systems are actually generalizing quite well, even for different postures of your face, right? So even if it's non-frontal, and if there's even if the face is covered, right? So here this is the same guy. Here again is the same guy. Here again is the same guy. So we see here the distance is smaller than if I compare these two, right? So I'm always showing here pairwise distances between the faces. So in practice, we actually have to set up a threshold, and I think usually for this method, usually the threshold is somewhere at 0.9, something to be sure that you are recognizing the person with good accuracy. Another way of using Siamese networks is for image retrieval. So image retrieval is like when you do, I don't know if you tried the Google search by images. So you can upload an image to Google search. Image search, and it will find you images which are very similar to the image that you have uploaded. And again, you can look at this as a similarity problem. because, well, again, we can have many classes. If you just think of landmarks, so you have a lot of landmarks across the world. Some of them are known, some are well, like the Eiffel Tower, or some are less known. For example, the front of my building, and you can actually use what you care is a good representation here. What you want to have is a good representation that will generalize to different types of classes. So it will be kind of agnostic to classes, but it will recognize your image based on the visual patterns that are inside there. So in image retrieval, that's what we do. We train with pairs of images. Usually you can extract this information for cheap because many images have their GPS. So based on the GPS, you can say, well, around a certain area that these images correspond to the same landmark. So this is a positive pair, and then you take a negative one, which will be from another country or from another city. But if you want to be a hard negative sample, you would take something from the same city, maybe from the neighborhood nearby. And this will be something really difficult because the network will have to not just guess the city, but actually guess the building itself. And here, this is one is quite typical to be trained with triplet loss. Another application of triplet and Siamese losses is in learning patch descriptors. So we can look at so patches are some small subparts of the image, and we can usually traditionally in computer vision we were using some handcrafted descriptors. Practically, we were looking at the pixel gradients and putting them into a histogram, but which is still a very strong method, but you cannot learn too much because it's quite handcrafted. And again here, because since they are small images, so usually a patch can be somewhere around 40 by 40 pixels or 60 by 60 pixels, 64 by 64. You also deal with it with a neural network. And again, this makes even more sense because, well, these local patterns, you have hundreds of billions. I mean, it's a lot of patterns that you can potentially have in the world. And well, doing classification on them is not obvious. So just to show you where we actually use these patch descriptors. So we're specifically using them when we want to match two images, right? So we have these here two images of the same cathedral with different zooms, and we have patches at different scales. You can see them here, and the idea is that we would want to match them and to find the correspondences between them. And usually, what we do, we take the descriptors of a patch here, and we compute the distances with respect to all the other patches in the image. Then we take this one and so forth, and then we manage to select the best corresponding ones. And well, just to give you an idea what's the output of such a thing is, you can see that we can match interest points quite well. Well, with some manual tweaking, but they still rely a lot on the quality of the descriptors for these small patches in order to better align the images. And then this can be used to construct 3D models of the world. So we call this structure from motion. You might have seen some demos like that. Practically, you take a dump of Flickr data, or well, usually it's Flickr, from a certain city with all the geotag images that you can find there. It's usually in the orders of thousands, tens of thousands, hundreds of thousands. And well, you give them to a server, and then the server extracts these local features, ideally with a neural network, and then you make a lot of computations of similarities between images, each one with each one, and well, there are some mechanisms to infer the 3D structure from these images, and this is usually quite accurate. As you can see here I have a model from Prague, and it doesn't use whatsoever any maps, or so just some weak GPS information from the photos posted on Flickr. And finally, another application for this is person re-identification. So it's kind of similar with faces, with face verification, but here this one is particularly used by, for example, for security, to track a person, well, a suspect after I don't know, an attack or a violence in a train station. You can actually, well, if you have a photo of that person, like this query, you can actually search inside all the video streams on your video surveillance system to identify this person. So to train it, again, we train it on different pedestrians like that, different persons like that, and it's the same principle: positive pair, negative pair, and eventually you will have this model that finds useful features that allows you to recognize persons with different dressing, different backpacks, and well, things like that, shoes and so forth. So this is some typical examples of how good this thing can work. So this is the query. These are the images found in the dataset. Well, I think it's a Chinese dataset in an outdoor market where you can track people. Well, they had multiple cameras and they annotated to recognize the people that wander around there. Okay, so actually we can go beyond triplets and in pairs, because you may have guessed, well, since we did the step towards triplets, what stops us from going further? So and indeed there are some people that said, look, we have these big mini batches. What if we considered all the other images in the mini batch except for my positive pair as negatives? So actually that's what they do. Instead of having just so if I'm looking here at the triplet loss, so I have here my anchor, a positive and a negative, and I'm always trying to adjust them with the two samples at once. The intuition here: what if I have many more negatives? Wouldn't it be more easier to just repel these many more negatives while attracting this positive? And apparently, yeah, you can do that. So it's practically a generalization of the triplet loss with n-pair loss. And we fetch these negatives just from the mini batch, so it doesn't come with an extra cost of having even more mini batches or more Siamese networks. It's just you recycle more the negatives in better. You use better the negatives in your mini batch. And another extension to that, which is called histogram loss. So here we have an input mini batch with different types with images from different classes, and what we do here, we compute all the similarities between all these images. We know from the ground truth which images come from the same class and which come from the other. And what's happening here, after computing all these similarities, we group in a histogram the similarities for the positive ones, and in another histogram the similarities for the negative ones. And they have this so-called histogram loss, but they use some tricks to make this the approximation of the histogram differentiable, such that it will allow it to repel the statistics from the two distributions. So ideally, the similarities or the distance, well, let's say if it's similarities, it should be close to 1. So if it's similarities, they should be all concentrated here. While if it's similarities for negatives, so these are for the positives, they should be all somewhere in this part here, where there will be less similarity between these two. So if it will be in terms of distances, it will be a bit the other way around. For positives, you want to have a distance close to 0, and if it's a similarity, the similarity should be as big as possible. Yeah, these well, depending on the loss, some people use the distance, and some methods use the similarity. So I'm just wanted to share with you a trick that can be, because we've discussed so far what we do when we have few labels and many classes, but what we do when we have few classes and few labels. So this is a problem which is called few-shot learning, and here we kind of also take inspiration from Siamese networks. And one of the most common approaches for this is what we call prototypical networks. So here the approach is really simple. So let's say that we have five images per class, right? And you want to train a network. So here I have 1, 2, 3, 4. Let's say that I have 4 images per class, though here I have also 5. So no, it's 5. I miscounted, sorry. So we have these 5 images. So what we do, instead of, we cannot actually do classification because we don't have many samples. So what we do, we say that we want to generate a good feature. So what we do, we generate a class prototype vector, which is practically the mean feature vector of the training sample. So I have here the green class C1. I have 5 vectors corresponding to my training samples. I compute their features with the network, and I do an average, and this is my prototype. Same for the orange class C2, and same for the correspondingly for the blue class C3. So instead of doing a regular classification, what we do when we have a new sample, we compute the distance of this sample with respect to all these prototypes. So I will have here 3 distances, and then I do a softmax on the distances. So I have minus the distance, and I divide by the sum of all the negative distances to have some notion of similarity, and then I'll have the class with the highest similarity or the smallest distance will be indicating me the best, the closest class. So since I have actually here I have so what will be the connection with Siamese networks here? So once it will be because of these prototypes, and I do the distance with respect to them, and actually what's happening here is that actually the gradient flows through all of these items, right? So since I'm doing just an averaging of the features from a certain class, there's a gradient passing by through through all of these samples. So I'm practically learning from all the samples that I have at the time, and it's quite convenient for future learning. So to conclude, so the main takeaways from Siamese networks is that there are a specific type of architecture which is particularly suitable for representation learning. So we don't want to focus necessarily on classification, but how do you do to have good features that will eventually generalize to some other classes that you may not know? It's quite useful when you have many classes and a class imbalance. So I would recommend to use Siamese networks there. And well, if you have just regular classification, well, standard settings with, I don't know, 10 classes or 100 classes and some images, I would still advise to use classification, which is a bit easier. And we have seen it's an important area because in the past 2 years, many modern methods leverage Siamese networks for unsupervised learning. And, well, they kind of invented the task there where since we need unsupervised learning, we don't have the labels of the image. So what the task they invented there to make it also like a contrastive loss. So they take one image, they apply strong data augmentation on it. So we have now 2 images. And you have a lot of other images from the dataset. And the goal here is to recognize, if you think of the negative pair loss, the M-pair loss, you pass all these images together through the network. And the goal is for your network to learn to recognize this image among this large pool of negatives. And actually, this works quite well in the past years. We've seen that it improves greatly the unsupervised or self-supervised learning that we'll find out, we'll discover in 2-3 weeks from now. So this is it. So I'll see you soon in the practical and also on Discord for the questions. Well, goodbye and see you soon.